All right. Sorry about this. I just realized that my slideshow was not showing. I don't know why it cannot see the slideshow. So I might have to now do it manually inside inside the application. So my apologies for it. I don't know why it can't show the slideshow of this. Okay, so let's run through this. I hope it's wide enough because is the screen very, is it wide enough? Does it cover enough area? Anyway, I'm a knowledge engineer. You know, I help cities, government organizations who are undergoing digital transformation towards data-driven operations to exploit their data assets in capturing information needed to simulate human decision-making and high-level cognitive tasks that can be used to solve complex problems and achieve their set objectives. So I've been doing software engineering for over 20 years and at least 15 years in data and 12 years doing semantic AI. I co-founded Nigerian earliest startup in 1997, and I'm passionate about smart city, urban planning, behavioral science, data analytics, pure and applied sciences, knowledge representation, data modeling, and augmented intelligence. All these things has to do with data, in the application of data. Now, for us to talk about network data analysis, we are going to talk about things like graph theories, graph analytics, study on French trains using R. Now, what is network and graph data? What is network data and what is graph data? So the promise of network analysis is the placement of significance on the relationship between actors, what you can call entities. So every data has entities about it. So network analysis is about the relationship between these entities, right? The data, not in individualistic nature. So it's about relationships and connections of all these entities. That's what network data analysis is all about. Now, the emphasis on complexity and the creation of algorithms to measure these various aspects of networks, because networks is about connections, okay, makes network analysis a central tool for digital humanity. So humans generated is key that we do network data analysis to understand, the complexities of humanity, in this. And that's what we are all going to talk about. So network analysis is a technique that uses graph theory. If you don't know about the graph theory, you need to read it up, but I'm going to talk about it in a few seconds. Graph theory to study complex real-world problems. So this is a problem-solving technique, okay? And we are talking of problem-solving in such areas like computational biology, engineering, finance, marketing, neuroscience, political science, and public health. So we can use it to solve problems, different kinds. We're going to emphasize on those problems. That's why this data analysis is very key that we understand it. Put relationships between objects in a group. Like I mentioned, every data has actors, or they have entities, or they have objects. This relationship, you understand, matters a lot, okay? So visually, we think graph as a series of interconnected circles. representing a member of a group, as people in a social network. Okay? So lines drawn between the circles represent a relationship between members, such as through friendships in social network. So now you get an idea what network data is all about. So graph analysis helps, or network data, in figuring out things such as influence of a certain member, or how many friends are in between two members, you know, something like that. Talk about graph. Yeah, so graphs are mathematical structures used to study relationships between objects and entities, okay? And then a graph is a set of nodes. You know, we talked about, these are nodes, you know, the A, B, C, D. It's key that we understand these things, okay? Another word for them is vertices, okay? So, and then we have what we call the links. The links are these lines. These are the relationships, okay? D and C, B. And these nodes are entities. So if you remember your English language, what we call noun, name of anything, places or things, okay? Those are nodes. So this could be human being, this could be cars, this could be cities, this could be markets, this could be anything. So relationship, connection, that's all, you know, the network data analysis is all about. So conceptually, we can calculate what a graph is G, which is the vertices, which is also the nodes, and the edges, which is also the links between them. That's what makes up a graph. So this makes up a graph. Then when we have graph G, we can get all the vertices of the graph. So all the vertices, what are the nodes? List of all the nodes. Then the edges. Now we need to keep this in mind because we are going to come back to it. All right? So this takes it further. Again, a sample data network, you know, vertex, edge, that's another name. That's this, okay? So these are components of it, all right? Okay, so again, we are all on the, you know, for us to understand what nodes are. You know, nodes are one of the two most important properties of a graph. Yeah. They are an entity. You know, they represent or a connection. This could be a person, a location, a product, an idea. Anything can be represented, you know, with a structure like this or similar structure. Now, edges are the second most important. So you see, they are connecting. There's a connection, you know, between the two. Because in your analysis, you want to understand the relationship between this and this, and what does this relation and this connection mean. So visually, it is usually represented as a line connecting the nodes or vertices. Okay. Now we have the graph. So the other things we don't want to know. We want to know the weight. It's a numerical action. We can put it in those relations, so that we can compare between two relationships. So this is relationship one, this is relationship two. So we can put a weight, you know, based on the text. You know, this is just to give you an idea of what you can do with a graph and why a graph or is very, very powerful, which we are going to see in a few minutes. Then the other concepts, you know, like neighbors. So neighbors are two nodes connected by an edge, okay? And a path, neighbors are two nodes connected by an edge. So these two are neighbors, okay? A path is a route or a route or edges or more nodes. So this is a path, okay? Because you are moving from, you cannot say point A to B in graph, so you can say point A to C. So because these two are already connected, so they automatically has a path. So you're not looking for a path for two connected nodes, but you are looking for a path from the third node. So it could be that you are looking for this path from A to E or from B to F. So this is where you need a path. So a path is a route between two, remember, between two or more nodes, okay? Then directed graph is a graph where each edge has been associated with an ordered pair of vertices. So we are talking about direction now. So you can emphasize that the relationship is not two ways, or that the connection is not two ways. You can say it is one way, which is directed, and two ways if it's unidirected. Okay? Now, many practical problems can be represented by graph. Like I said, this is a problem-solving or problem-solving tool that have been used to model problems and situations in, okay, including physics, biology, psychology, social networks, communication, information network, transportation networks, computer science, even your electricity networks. Okay, so there are so many things. So graphs are used to represent networks of communication, data organization, computational devices, the flow of computation, even the flow of water. Okay, that's to just tell you how powerful a tool is. And I use it. I use it in my day-to-day work as a knowledge. Where is the origin of graph theory? Now, this is a very interesting thing. So we have what we call the problem of 7 bridges of Connect. It's a city in the Prager River in Prussia. That is in the old Russian republics or USSR. So there were 7 bridges in Kaliningrad connecting 2 big islands surrounded by the Pregovia River, and the 2 portions of mainland divided by the same river. So the 2 portions of the river, this is the river flowing, and then you have these 2 islands, W and surrendered, yeah. So W and Y. So the problem with the Königsberg Bridge was to be able to walk through the city by crossing all the 7 bridges only once. So you can see here there are 7 bridges, 1, 2, 3, 4, 5, 6, 7. So this was where the graph theory came up. How can you cross, how can you walk through by crossing all 7 bridges only once? That's what the graph theory did. So you can see, the map better illustrated. See if you can walk through the city by crossing each bridge only one. There should not be any bridges. Each bridge must not be crossed more than once. That's the rule. This is a network data analysis problem, okay? And this is where everything started. So Leonard Euler solved it in 1735 by proving that it is not possible. He found out that the choice of a route, each land area, is irrelevant, and that the only thing which mattered is the order or the sequence in which the bridges are crossed. He had formulated an abstraction of the problems, eliminating unnecessary facts, focusing on the land areas and the bridges connecting them. This way, he created the foundation of graph theory. So if we see a land area as a vertex, each bridge as an edge, we have reduced the problem to a graph. Now, I don't know whether you got that. So this is the map, and then this is the graph, the visual graph. So each of the land areas of the city are represented as vertex, as you can see here. So the vertex are W, X, Y, Z. So look at it, W, X, Y, Z. Then the bridges are these connections. Okay? Now, if you look well, you will see that there are 7 connections for 4 land areas. Like you can see, it is now labeled E1, E2, E3, E4, E5, E6, E7. Okay? Now, this is how this, so think about this for a minute. The problem. This is the solving sequence. All right? So, okay, yeah. So the way he said it was that, again, if he found out that the choice of a route inside each land area is irrelevant, that the only thing that mattered is the order or the sequence in which we are crossed. So we didn't really, the solution wasn't really about, wasn't really about following the rules of going through the bridges once, but it's about the best way to go through all these locations. So what he did was that he now moved, let's say from X to W, which formed the root 1, and he went back into X. Oh, sorry, no. So it went 1, then 2, then 3, then 4, then 5, then 6. Okay, yes, so we had to repeat a bridges more than once for him to do the 7. There was no way he could have done that, but you can now understand that with this, it structures the way we create our answers. It structures the way we create our answers to solutions that we have. Okay, so to go to other terminologies before we start going into algorithms. So I talked about, undirected graph. It doesn't have any particular direction. Directed has a direction on the graph. Connected graph, a graph where there is no unreachable vertex. There must be a path between every pair of vertices, okay? Disconnected graph, a graph where there are unreachable vertices. Finite graph, blah, blah, blah. I think we can go through all this. The presentation will be made available. So again, undirected graph, you can see it here. And then you can see directed graph. So the directed one has arrows, it shows direction. This one doesn't show. Okay. So why are graphs? Why graphs? So graphs are a fantastic way to represent and visualize the relationship between entities. But this isn't their only purpose. Graphs are usually built to provide a unique data structure to perform calculations upon. As we have seen about the bridges, we have put it in such a way that we can easily start calculating things. So graphs provides a better way of dealing with abstract concepts like relationships and interactions. They also offer an intuitively visual way of thinking about concepts. So, you know, in our minds, when we think about ideas and concepts, we are thinking about, you know, mind maps. You'll find out that your graphs, maps, okay? So this is why it's a powerful tool, right? So graphs form a natural basis of analyzing relationship, like in social context, you know, like in social media, okay? Now, graph databases have become common computational tools and alternatives to SQL and NoSQL databases. So graphs are used to model analytics workflows in the form of directed directed acyclic graphs. Okay. We also have which we normally call DAGs. Okay. So we do have neural framework, network frameworks, which also use DAGs to model various different layers. So this is all down at so many reasons why, you know, the graphs are very powerful. They power a lot of machine learning algorithms as well, and all computational efficiency, you know, that we cannot get in tabular data structures. Okay, so graphs can be built from any data that has relationships. Usually, every data has relationships. So all the flights to and from airports can be organized as a graph. Now we're going to treat this as a case study later on in using R. So in this case, the airports are the nodes, and the flights are the edges between the nodes. We can also use accounts of a bank. You understand? And the money transfers. Accounts are the nodes and transfer are the edges. All deliveries between addresses worldwide can be organized same way. A visitor journey on an organizational website can also form a graph where the web pages form the nodes, the visitors' movement become the relationship. In retail, products can be the nodes, and the purchases become the edges. So it's a problem-solving technique, and the Gartner, this is old, by the way. I wish I got the latest one. You find graph analytics here. So it's heading up to the plateau of productivity. So it's coming down here. So it has gone beyond the hype zone and, you know, very powerful. So by now, it will be at the trial of disillusionment, which is where by now all mistakes should have been done, and then the slope of enlightenment coming up. I suspect that the graph will be here by now. Okay. Look at it here. The graph is down here as well in 2020. Okay, so it's moving. If you look at it here from 20, the graph is here, 2019, is now here in 2020. All right. Now let's talk about the algorithm, you know, about all these things. So this is all about graph, network data. Now we have different techniques of extracting value from this. These are the algorithms. So graph theory is the dark horse of business intelligence. It comes in many names. and variations, social network analysis, network science, network theory, network data analysis, but they all have the same algorithm. Okay, so we have what we call graph traversals, which are a means of every vertex of edge and edge. So your algorithms must visit every node or edge or vertex and edge in a well-defined order. Okay, so while using certain graph algorithm, you must ensure that each vertex of the graph is visited exactly once. Everything must be visited for it to claim to understand what's in the graph. So we have what we call, during traversal, we have two major ones. We have what we call the breadth first search, which is BFS. Then we have the, which is DFS. There are two different algorithms used to search for nodes in a graph. They are typically used to figure out if we can reach a node from a given node. So we want to know, for instance, a flight. How can a flight move from Lagos to Ukraine? How can it move from Lagos to Ukraine? So this is already a problem that everybody knows. This is what your travel agent, the software that they use, this is what they use, because airlines database is graph. So they are typically used to figure out how to reach a node from a given node. So how can a node, Lagos, Kyiv is a node. How can Lagos, somebody in Lagos, reach? We all know that there is no direct flight. So it's going to search every other airport to find the shortest, the longest, the fastest. Now it starts making sense what graph data can do. The aim of the BFS is to travel the graph or traverse the graph as close as possible to the root node, while the DFS algorithm aims to move as far away possible from the root node. The root node is the first node in the graph. Okay, so you can look at here. This is the root node. So for the BFS, when you start traversing, you start traversing from here, and it goes down. You see, it goes down. This is now where what we define as a path. It goes from this node to this node. It goes to this node. No, it comes back up. It comes here. It goes here. You know, it comes back up. It goes here. It goes there. You must visit every. So remember the bridge problem. The bridges problem. This is, now you can see how this traversal works. And this is how we want to look for, this is Lagos, and we want to move to Kyiv, which is the fastest way to move to Kyiv. Okay, so maybe we have here London, Madrid, and Poland here. And later we will now find out that going through Poland is faster to Kyiv than going through London. This is what happens. Okay? The same thing about the depth first, you know, is the opposite. You know, it moves away from the root node. Okay? So you can see the difference between breadth first and then depth first and then the breadth first. It traverses through the left subtree first and then traverses through the right subtrees. That's for depth first. Then the breadth first, it traverses through one level of children, nodes, then traverses grandchildren, nodes in each. I don't think this diagram catches. Let me see. There should be. This diagram doesn't catch the depth first well. Try to update it. Let me take that depth first again. So the depth first algorithm is a recursive backtracking. It involves exhaustive searches of all the nodes by going ahead of possible else by backtracking. Pick a starting node, push all adjacent nodes into a stack, then pop a node from a stack and select the next node to visit and push all its adjacent nodes into a stack. Repeat this process until the stack is empty. However, ensure that the nodes are visited are marked. What it does is totally opposite of this. Okay? This goes in, this goes into the first layer. And then starts checking the children layer first, right? It checks it, so it goes from 1 to 2 to 3, then goes to 4. So it does the first layer first, and then 2. Now, depth first is the opposite. It goes from first layer, it goes down, and then comes up again, goes down. So it checks everything here first, then comes back up there, and comes back here as 5. Okay, it gets, yeah. So it comes back here as 5, it does this and 7. Why I said this doesn't capture it is because that, okay, it still got it right. Okay, I was the one that got it. There should have been an arrow here to show that it must go from 2 to 3 before coming to 4. So this diagram is not the best for it, but this one captures it perfectly for depth first. And then this diagram here captures it for breadth first. Okay? Though this breadth first here is numbered well, but the arrows were not very obvious. So let's move on. So now let's go to one of the most important algorithms. So now we are taking the algorithms that we use to find out the value in each of the graph data or the network data. So this is network data analysis right now. So one of the most widely used important conceptual tools for analyzing networks. Centrality. The centrality aims to find the most important nodes in a network. There may be different notions of importance, or for important, and hence there is what we call the centrality measures. So the centrality measures themselves by having a form of classification that's adding more context. Measures that are characterized by flow along the edges are those that what we call a work structure. Okay, so if you go back to a node like this, a structure, what is centrality? Which of these things, which of these nodes is the centrality looking for the most important node? The most important node, the node that has the biggest influence on all this. We need to know. So let me give you a classic. A classic case is a bus stop. You need to know your centrality to know your most influential bus stops. If you're in Lagos, stops, Oshodi, CMS, Yaba. These are bus stops that have influence. They can take you to a lot of part of Lagos. So when you do a centrality analysis of traffic of bus stops, your most influential bus stops will always turn up one of these: CMS, Oshodi, or Yaba. Okay? So the centrality metric comes in many flavors, with most popular including degree, betweenness, and closeness. These are used to calculate the importance of a particular node, and each type of centrality applies to different situations depending on the context. Like I said, that is about adding context to the whole centrality algorithm. So centrality of graphs can serve as indicators of finding the most. If you are not understanding this centrality measure, don't worry. The most important thing, once you start, you will start asking questions of how much more you want to get out of your centrality. Okay, we are going to talk about each of these measures soon, in a few. So centrality of graphs serve as indicators of finding the most important or most influential vertices or nodes of a graph. An example, centrality measure will allow analysis of the most influential papers in a network of publication, cross-citation, co-authorship. Given the above example, a bibliographic knowledge. So you want to know the most influential, who is the person that has been cited the most, who has co-authored, who has published. It shows influence on a subject. That's how you find out thought leaders. Who is the most influential person in papers generating new knowledge in a new place? Okay, so the first, conceptually, the simplest centrality definition is the number of edges connected to a node. In this case, now look at what I said. Number of edges connected to a node. So the more edges a node has, now this is why I'm telling you that once you understand the centrality, you start asking more questions. So the more you find out that nodes have a lot of edges to it, that's some form of power. Why are we saying the Yaba, CMS, and Oshodi bus stops are your most? Because they have a lot of edges. A lot of bus stops are major bus stops. I use this in trying to make a city computational. One of my work is, for instance, turn Lagos. Now, this is what network data analysis is all about. One of my work is location like Lagos into a computational model. So that means everything can be calculated. I can calculate the flow of water to people's houses. I can calculate how quickly people can move from their houses to their place of work. I can, determine how long traffic cost Lagos people. So many things. So that's why this network data analysis is a very powerful tool that everybody needs to know. You can create a lot of careers out of it, just only on this. So inflow and outflow. So we can have 2 degrees of central measures in the case of a directed graph. Now look at the word now, directed graph. There might be bus stops that can, flow their passengers to the big bus stops, but the big bus stop does not go to them directly. Think about that for a minute. Okay? Then you now understand there can be different kinds of powers. So these values can determine whether a node is prominent with lots of other nodes reaching towards it, or influential with the node itself reaching out to many nodes. It's very key. Algorithm, centrality. So prominent, even if you look at it from a lot of, you see that a prominent node can be a good leader. And if person is somebody that can be a good teacher. That means if you are looking at it from a human being point of view, you find out that you're a prominent person can be made a good leader. An influential person can make a good teacher. I mean, now it gets more interesting. This is so powerful that a lot of things in the world today, created today, comes out of this centrality algorithm. So a node with a high degree of centrality, which is a node with lots of edges, is generally considered highly active node. If the graph represented a network of flights between the airport, then the airport with the highest degree of centrality would be the busiest airport in the world. Now think about it, that the busiest airport in the world is most likely London, maybe a little bit of New York. So that's London could be said to have the highest degree of centrality because everybody comes to London, everybody passes London. All right. So a country will want their airport to have a high degree of centrality. That means this is how the economy boosted, because a lot of people are coming in into, you know. Now, betweenness centrality is the measure of how often a particular node lies on a shortest path between two other nodes. Let me say this again. Betweenness centrality is a measure of how often a particular node lies on a shortest path between two other nodes. A high betweenness centrality will suggest that removal of that node will increase the distance between a lot of other nodes. Now, let me give you an example of this. An airport. We have airports, like we have Lagos Airport that takes in most of the flights. You need another airport to serve as a secondary airport so that people can go to that airport, land on that airport, and take other means to get into Lagos. It is nearer. The prices will be a little bit cheaper. So it gives an option. So people will be looking for other. Lagos flights are fully booked. Why don't we look at Abeokuta flight? Abeokuta Airport, which is the closest airport to the Lagos Airport, or we can say the Lekki Airport is the closest airport to Lagos Airport. So this is a very good example of that. So if the graph represents between airports, all airports with high betweenness centrality will likely make an excellent layover or connecting airport, because the line between the two indirectly connected airports. Okay? So there are reasons for that. Okay? There are reasons for that. So you can look at here, this airport. This is why we have weight. So we can put weight as distance between this airport. So distance from here to here is 9. And the distance from here to here is 6.5. Okay? Now you can see here that this is shorter to here than this. So this is your betweenness centrality. Okay? This is how we calculate distance. You understand? Now, closeness centrality, a measure of proximity of a node to other nodes. A node with a high closeness can broadcast information quickly in a social network. A person that has high closeness centrality is an important person. In the context of network of flights, the airports with the high closeness centrality will most likely have lots of quick, small flights, outbound and inbound. So you want something that people can easily, live, that is close by, but not necessarily in competition. That people can easily, move away from a node, not so dependent on a node. So we can decide to have, like, by the international airport, we have local airports. So now that we can take people right into the country. We don't want to use international to move people into the country. So we have a smaller local airport that can move people into the country. Okay. When it comes to a social network, the person that has a high closeness centrality is an important person. It's an important person because it is close to the most influential person. So that person can be directed for questions. You don't have to exert so much pressure on the most important person in the social network. So closeness centrality has been used in studies to recognize individuals in positions to control information and resources within an organization. It can be used as a metric for estimating the arrival times of package deliveries, to calculate the importance of certain words and phrases in documents, okay, using graph-based key phrase extraction. So in document extraction, you want words as close as the main words, okay, because that represents the word, So we are talking about synonyms. Synonyms are closeness centrality to words, right? Okay, so this is a visual to explain what we've all talked about: degree, betweenness, page rank. We never talked about page rank, and then closeness. Okay, you can see betweenness, a lot of nodes coming to it. Degree of centrality is has a number of connections to it. Closeness is, you are talking of close to centrality, the one that is close, that has its own interests as well. Then page rank, which node is the most important? So we've mentioned something like that, but I think we're going to talk about it in a few. So yeah, so this is the same thing. So this is just talking about the difference between the different kinds of centrality. You can go through that in the graph. It was the first algorithm used by Google to rank websites in search engines. So that one you already know. Page rank algorithm is based on the premise that the importance of a node depends on the importance of its neighbors, which in turn depends on the importance of their neighbors, and so on. So for instance, in neuroscience, the page rank of a neuron in a neural network has been found to correlate with the relative firing rate. And in ecology, page rank can be used to determine species that are essential to the continuing health of the environment. So we also use this one to know page rank is also used in COVID, finding cure for COVID as well, finding the right, important elements in your body. So this is how a page rank is, with a site, knowing which pages are important, and they are ranked. So there are so many There are so many algorithms. We have the associativity. It measures the preference of a network node to connect to others that are similar in such other ways. So social networks like Twitter and Facebook provide a heap of proof of associativity, uncovering hidden insights in big data. Okay? There are so many. Shortest path. We want the shortest path to move. So you use shortest path is the most often used algorithm. We use that like in our Google Maps, in your boat, your Uber. It uses the shortest path. Distance between two locations is a graph. It's a graph problem. Okay, so we have the shortest path. You can look at it. The graph for a shortest path, they're all weighed. So what is, if you look, if everything is weighed, what is the shortest path, you know, to 7? So if you do the calculation, the shortest path was 2 plus 8, 10, 11. If you take this route, it will be 2 plus 3 plus 10. 2 plus 3, that's 15. So that's not short. If you take this route, it will be 16 plus 3. That's short. If you take this route, 6 plus 5 plus 3, that's 14. It's not that short. So you already know how that works. Now, I'm being told I have 15 more minutes. So let me rush because I need us to that case, because this is for the our ladies and I need everybody to pay attention to the case study. So what the graph mean? Let me see whether it's not one of the most important. Then we have the graph center. Now this is another good algorithm. This was used by the Benin Empire, that's Benin City, in the year 1545. The Benin City was the first smart city in the world in the year 1545. They built their Oba's palace in the center of the city. It is a set of vertices of minimum eccentricity, that is set of all vertices where the greatest distance d to other vertices v is minimal. You know, so if you look at it here, it's at the center of town. For instance, a hospital should be placed in such a way that an ambulance can get as fast as possible to the farthest situated house. You want to place your ambulance in such a way that nobody is cheated in a city. So that's the graph center algorithm. We have community structure. We have path of flows. I think you have an idea about this. We have vertex similarities. There exist measures of vertex similarity that captures the relatedness of nodes in a graph by considering the neighbors they have in common and specificity of the paths that exist between them. So this is about finding similarities. I think you can figure out why we need to have similar, why we need to know similar vertexes. Now, this is another powerful one. Consider communication stations and a list of possible connections with them, having different calls. So find the cheapest way to connect these stations in a network so that the station is connected to any other. This may be used, for example, to connect villages to cable TV or to internet. So that's a powerful algorithm. So we have the Eulerian path, which was a path used to solve the problem about the bridges. Okay. We have a Chinese postman problem. So I'm racing down. There are many algorithms. There are many algorithms, so which you can read about. But I've dealt with the most important one. So analytics. Graph analytics is a set of analytic techniques that allow the exploration of relationships between data sets like organizations, people, and transactions. So you use it to uncover insights in networks of data. You use algorithms. All these algorithms I mentioned on the connect, and infer the organization and dynamics of real-world systems. Okay, now we have graph database that can do that, and which is talking about the semantic model, of words. So take for instance now this word, we send email to people so that they will visit our website and buy our product, can be presented in a graph like this format and stored in a database. That's what a graph database does. Okay. Now we have the differences between databases, different kinds of databases, relational, key, graph. Graph analytics allows us to answer questions like, is our network densely or sparsely connected? Who is the most connected person in the network? Which friends do have people in common? Okay, so I'm jumping all that to the business applications of graph. Graph can be used to figure out the most influential people in the social network. I think we talked about that. Graph can be used to find unusual patterns in mitigating fraudulent transactions, as you can see. Graphs can be used for optimal routes for your delivery. We've said that. Pharmaceutical, we can use it to solve the route for the salesman, knowing where they have. Graphs can be used by telecom industry to plan their stations. We've talked about how it is for the public transportation, and then the other example, network flows, algorithm. So now we want to come to a case study. I think I have like 10 minutes to go through this. So this is data for those. So since this is about I don't know R, so up some R just because of this presentation. I use Python for my own work. So and I'm not here to make the Python versus R thing. I believe R is very powerful at Python on data. So enough said about Python versus R. They are the same thing basically. I don't know why people should choose one for another. Anyway, so we got a French data, a trained data set, daily total trips per connecting station. So this is a link for it. And we are going to use these tools in our tidyverse and tidyverse adjacent. Okay. So as you can see, this is a data source, which you can see the year, you can see the month, service, the departure station, the arrival station, journey time, okay? Which you can, yeah. So, so to understand, this will help to understand how use the data to understand how stations connect with each other. A new summarized data set is created called routes, which contains a single entry for each connected station. It also includes the average time. It also contains the average. It includes the average journey time it takes to go between stations. Look at it here. This is the route. Okay, to generate you here from this station to this station, and then the journey time. Okay. Now, the next step now is to transform this into a graph. So in order to prepare this for transformation, we have to contain two variables, name, form, and tone, which are the names that tidygraph expects to see. So this variable should contain the name of each member of That's each member of these stations, and the relation, with the other stations. So it should have the relationship between this station and this station. Let's look at it now. So we have it here. So this is a directed graph, from one station to all this. Okay, there are more data to that. So, this is a list of all nodes. Okay, remember we did this at the beginning to show you that we can get all the stations. Okay, now, and this is all the information on the edge. All right, because if you look at here, the from and to, that's the relationship from number 1 to number 39, because they all have different numbers. Okay, there are up to 53 of them. Sorry, just to give you an idea. So the relationship, because all these ones have a number. Let me go back to the previous one, so you can see all the numbers here in the station. Okay, so now we are creating a relationship between each of these stations. How people flow from each of these stations. All right. Now, the root table now into 2. So we can now do a node data, which you can see here. Sorry, this is the query for you to split, into 2. So you now into the node. So you can see it here, the name of the station, the title. Okay, and this is the label. And then this is the node. All right, so now we want to now turn that into links, that into the relationship between the station. So if you look at the graph, you can already see a centrality here. This is a very powerful node. You can see a betweenness. You can see a closeness here. So that means people can stop at this station if here is full. Okay, there's so much you can see here. So you can also see that these 2 stations are the most powerful stations that we can see in this data. This train station here and this train station here. Okay, and people will be keen to find out the nearest station to this powerful station, anywhere where you can stop and take other means to reach here, just in case there are no available trains here. Okay, now you can see how powerful this can be. All right, so now we are putting a label. So we have decided to add those labels that we defined here. Okay, sorry, I think I jumped this graph. Yeah. Okay, so these are the labels. Sorry, I jumped a lot of graphs, but so we are putting a label, so that's what we're going to use. And then we're adding a legend. This one, the first one doesn't have a legend, so that's what we have here. So this is the station without a legend. So it's very clear. We can see very powerful. There's so much out of this little information. Then we've now added the label for us to see that this is Paris. And then there's Lyon nearby. Okay. So you can see how powerful these stations are, in the graph. So all these things can be done with R. Okay? And then, we want to calculate shortest path, and then it gives us this. Wait, this query. Yeah. So, we talked about stations, nodes that are on the shortest path. Okay? So it gives us this one, this station here, has been on the shortest path. All right? Okay, so we are now looking at the shortest route into uh, one of the stations, that is ARAS and MASI stations, that we have selected before, and then so that we can now change. I have to take this. I don't know whether I still have enough time, and just because I'm trying to rush, the whole graph is actually a story. I wanted us to move. We are creating, the shortest path between this ARAS station and Nancy. That's what this whole code is all about. So that what is the shortest way to go from here to this point? Okay, and that's what we have calculated here, and that's what is being plotted here. All right. So we can do so many things with the graph, including including finding the longest route and so on. So this is how we can do it with R. I'm sorry because time is up, and I'm just in a hurry. So in conclusion, understanding, using, and thinking in graphs makes us better programmers. Graph theory as a team for data analytics and data science is not a new concept. It's just that it's not popular, but it's something that we need, and I'm hoping that today most people will find it very interesting. I use a lot of graph theory, so people can always reach me and ask more questions. I have tried to pack a semester course into one presentation. So, so for us to appreciate it first, and then let it tickle our fancy and want to know more about it. So, mapping relationships among high volumes of highly connected data. Graph analytics unlock insightful questions and produces more accurate outcomes. This is a very powerful statement, and I need us all to understand. Graph data is very powerful. Making it's like looking for solutions to problems. So this is so there is that comparison between relational analytics, which is what we do with SQL, because it has a lot of one-to-one relationship or one-to-many relationship. But graph analytics is based on a many-to-many relationship. So they are totally different. So relational analytics restricts you. Graph analytics extends. So that's why it's very powerful. So we should really take it seriously and then use it to solve problems. So thank you for listening to me. My apologies for the rush, and also my apologies for why my um, slideshow. I don't know why he couldn't see my slideshow, but um, this is quite interesting, and the slides will be shared. Thank you very much.
All right, thank you. Let's say thank you to our speaker for today. I think that comes to the end of our event for today. Thanks for joining. So if you'd like to join our community, you are welcome. You can go to CMX Connect /Lagos. That's where you get information from, and we hope to see you at our next event. Thanks.